Earlier this year, I ate my hat. There's some things we said we'd never do. We're going to build a big rocket. It's called Neutron. Luckily for me, there are no hats on the menu today, but what I will be dishing you out is full details on the Neutron launch vehicle. We've been busy. But let me show you a new breed of rocket, where reliability, reusability and cost is hard baked into the design from day one. This is not a conventional rocket. This is what a rocket should look like in 2050, but we're building it today. So where do you start designing a new rocket? Well, ironically, you don't start at the rocket. You start at the satellite and all the spacecraft that you need to launch, and then you start the design process around that. Over 80% of all of the satellites that are going to be built in the next decade are going to be small satellites and constellations. And these constellations form a critical part of the infrastructure around the planet to guide, monitor, and enable Earth's future. Constellations require very unique deployment needs, and up until now there hasn't really been a vehicle that's optimised to do that. But of course Neutron's not just great for constellations, it's great for geostationary deployments, human spaceflight, and of course my personal favourite, interplanetary. Now as we went through the design process, it became very, very clear that this rocket was going to dispense with all convention. So what does a rocket of 2050 look like? Well, let's start off with the absolute basics. This is a reusable launch vehicle, so that means it's got to land. So you don't want any deployable landing legs, you want a nice big wide static base. Next is the upper stage. The upper stage is actually really, really tricky because it has competing requirements. Firstly, it has to be the lightest and the most high-performing structure as part of the launch vehicle, but it also has to be the lowest cost, because for Neutron, at least at this point in time, it's a disposable upper stage. So when you think about making super light structures and super high-performance structures, you need to really put them in tension. So Neutron's upper stage is actually hung from the payload separation plane, which makes it incredibly strong, and it also makes it the lightest upper stage ever in history. Finally, we add tanks to the bottom of stage one and then connect it all together. Now, Electron's taught us a lot about reusability, and reusability and re-entry is not actually a structural problem, it's a thermal problem. So the best way to manage a thermal load is to just not have it. And if you look at Neutron behind me here, what you can see is a continually decreasing shape and size of the vehicle, starting large at the base to smaller at the top. That's actually really important because what that does is it decreases the pressure along the vehicle. So as we're re-entering the atmosphere, that decrease in pressure ensures that we don't have any shock waves attaching to it. So this is Neutron. It is an absolute beast. It stands 40 metres tall, it has a 7 metre diameter at the base and a 5 metre class fairing. And as you can see, we can lift 8 tonnes in a fully reusable mode, returning back to the launch site, or 15 tonnes is its maximum payload capacity to low Earth orbit. And the vehicle itself weighs 480 tonnes. So if you stood in front of a rocket in 2050, you wouldn't expect it to be made of normal materials. Weight is absolutely everything in a launch vehicle. So what we set up here is a little bit of an experiment. We have roughly 1 square metre of material here, and we've allocated 3.5 kgs per square metre of the rocket. Now stainless steel is quite a popular choice. Oh, that's not so good. Let's try some aluminum. That's not very good either. Okay then, let's try something new. Let's try carbon composite, but not any kind of carbon composite, a Rocket Lab carbon composite. Now that's what I call a 2050 material. But sometimes carbon composites get a bit of a tough rap because they're expensive to manufacture and slow. Not the case. We're going to do this fast. We're going to use automated fibre placement. 3D printing really changed the game when it came to rapid manufacture. At least it did in 2013 when we used it to build the first 3D printed rocket engines on Electron. With metallic 3D printing, you measure the speed in millimetres per minute. With automated fibre placement, you measure the speed in metres per minute. We have already shown with Electron that carbon composites are an ideal material for an orbital rocket. Now, thanks to Neutron, it's going to really come into its own as a rocket material of the future. Now, as much as I do love the sleek black look of carbon, it's about far more than looks. A huge reduction in weight is a game changer. If you can take the mass out of the rocket, you take the pain out of propulsion, and quite literally, the heavy lifting. Now let me introduce you to Rocket Lab's newest engine, Archimedes. Now, because we don't have to lift a great big hulking metal rocket into orbit, it means the engines can be far less stressed. We don't need to push the engines to their absolute maximum. Archimedes is a 1 meganewton thrust engine. With over 320 seconds of ISP, its propellants are liquid oxygen and methane, and the cycle is also very simple. It's a gas generator cycle. These are all the things you want when you have to build an engine that can be reused over and over again. There is no point in having an engine that is absolutely busting its bolts at 11,000 psi. What we need for a reusable launch vehicle is an engine that can run over and over again at very low stress and very high margins. That's what's important. Seven Archimedes engines propel the first stage. Since reusability is at the heart of the Neutron design, we asked ourselves, how could we reuse as much as possible to really drive down those costs and time to get it onto the pad and launch again and again? The answer is not throwing away the fairings or even trying to catch them. The best way is to never get rid of them in the first place. Next, we have to control the rocket during re-entry. So that's right, Neutron does not land on a barge, it is a return to launch site vehicle. So to guide the rocket back, we use the shape to our advantage, just like Electron. We use the atmosphere to do as much work as possible. Small control surfaces called canards at the front make small changes in the trajectory needed to get the accuracy and guide the stage back to the launch site where we started. So what lands back on Earth is a complete first stage, fairings and all. And all we need to do is open those fairings back up, load in a second stage and a payload, close the fairings and go again. So what does a 2050 rocket look like? Well, it should be designed to be reusable from day one. It should also have materials that are advanced, materials that can withstand all the forces of re-entry and are cost-effective and easy to manufacture. It should also have engines that are able to be used over and over again, and engines that aren't stressed to their absolute limit. It's really important also to be able to return the vehicle to a launch site, not costly barges way out in the middle of the ocean. And then finally, it's also important not to throw away fairings, but just have a vehicle that you can load upper stages and payloads in and fly again and again and again. And it launches from a pad without all that bulky and costly infrastructure. We did something extraordinary with our first rocket, Electron, and we're doing something even more extraordinary with Neutron. The team is flat out right now at full force developing it. Prototype tanks are under manufacture as we speak, and Archimedes will breathe its first fire next year. Because at Rocket Lab, when we say we're going to do something, we do it.